Have you ever thought about what would happen if everything stopped moving? This question brings us to the concept of absolute zero, a theoretical temperature where all motion ceases completely. Imagine a world where every atom stands still, frozen in time. That's absolute zero for you, a bone-chilling minus 273.15 degrees Celsius. But hold on a second, this is more of a theoretical construct than a practical reality. You see, in our universe, reaching absolute zero is as elusive as catching a shadow. Here's why. Temperature is a measure of motion at a microscopic level. The more an atom jiggles and jives, the hotter it is. So when we talk about absolute zero, we're talking about a state where atoms lose their groove, they stop dancing. So if all motion stops at absolute zero, what does this mean for the energy within a system? Let's keep exploring. Enter the third law of thermodynamics, a principle that has profound implications for our understanding of the universe. Now let's unravel this lofty concept and make it a bit more digestible. The third law of thermodynamics, in its most basic form, states that the entropy, or disorder, of a system approaches a constant value as the temperature of that system approaches absolute zero. Picture it like this. You've got a room full of bouncing balls, each one representing a particle. The more they bounce around, the more chaotic or disordered the room becomes. That's high entropy. Now if you could somehow cool the room down to absolute zero, the lowest temperature possible, all those bouncing balls would come to a standstill. That's the image of perfect order, or low entropy. But the third law tells us, quite firmly, that we can't actually reach that state of perfect order. As we cool the room, the balls will slow down, but they'll never completely stop moving. That's because absolute zero is impossible to reach. It's an elusive theoretical limit that always stays just out of reach, no matter how advanced our cooling techniques become. So what does this mean for entropy? Well, it means that there's always a certain minimum level of disorder in any system. Even at close to absolute zero, there's still some movement, some unpredictability. Entropy never quite hits zero. This has some pretty significant implications. It means that there's a fundamental limit to how much we can know about the microscopic details of a system. No matter how hard we try, there's always some level of uncertainty. It also has implications for the flow of time. The fact that entropy always has a minimum limit means that there's a direction to time. We can't reverse it because that would mean decreasing entropy, and the third law says that's a no-go. In simpler terms, the third law tells us that absolute zero is an unattainable goal, and entropy always has a minimum limit. So how does this abstract concept affect our everyday lives? Well, the third law of thermodynamics might seem far removed from your daily routine, but it has real-world implications that are closer to home than you might think. It's a guiding principle in refrigeration and cooling systems, for instance. These systems rely on the principle that heat moves from a hot body to a cold one. The third law helps us understand the limits of these systems, dictating that no matter how efficient our technology becomes, we can never cool something to absolute zero. Now let's talk about the study of materials at very low temperatures. This is a fascinating field where the third law plays a crucial role. As substances get colder, they tend to behave differently. Some materials become superconductors, allowing electricity to flow without resistance. Others become superfluids, flowing without friction. These intriguing phenomena can only be fully understood with the lens of the third law of thermodynamics, but perhaps the most captivating application is in the realm of cryogenics. This field is all about reaching temperatures as close to absolute zero as possible. You might be thinking of cryogenically frozen humans, but it's mostly used for preserving biological samples and superconducting magnets. Scientists in this field use the third law as a roadmap, guiding them towards these extremely low temperatures. It's an exciting journey, but one with a clear boundary. The third law of thermodynamics is like the ultimate speed limit sign in the universe, reminding us that absolute zero is a destination we can approach, but never quite reach. This might seem disappointing, but it's also a testament to the power and the mystery of the universe we live in. Even though we can't reach absolute zero, the third law of thermodynamics guides us in trying to get as close as we can. So what have we learned about the third law of thermodynamics and absolute zero? In the past few minutes, we've embarked on a journey exploring the fascinating world of thermodynamics, specifically focusing on its third law and the concept of absolute zero. We've scratched the surface of an intriguing scientific principle that governs the natural world and the universe at large. The third law of thermodynamics, to recap, states that the entropy of a perfect crystal at absolute zero is exactly equal to zero. In simpler terms, it means that all systems disorder, or entropy, approaches a constant minimum value as we get closer to this elusive absolute zero temperature. But what is absolute zero, you may ask? It's a theoretical state where matter stops moving entirely, a point on the temperature scale where no further cold is possible. It's pegged at 0 Kelvin or minus 273.15 degrees Celsius. Quite chilly, right? But here's the catch. While we can get extremely close, reaching absolute zero is a Sisyphean task. It's not practically possible due to the laws that govern our universe. This ties back to the third law of thermodynamics. As we cool a system, it gets exponentially harder to extract the remaining heat. In other words, the energy required to remove the last bit of heat increases infinitely, making absolute zero an unattainable state. This law isn't just a theoretical concept, it's a fundamental principle that impacts various scientific fields ranging from material science to quantum mechanics. It gives us valuable insight into the behaviors of different materials at low temperatures and helps us understand the limitations and possibilities within the realm of scientific exploration. In the grand scheme of the universe, the third law of thermodynamics reminds us that there are limits to what we can achieve, but also that there's always a minimum amount of energy or chaos in any system.